trying to use this podium computer, but it's not a smart screen. Okay, let's can hear now. Okay. Let me stand here. So you have 3 terminals. 2 are for the inputs, 1 for the output. So this is a kind of a mathematical symbol because it did not show 2 other symbols. One is ground, the other is a power supply. So ideally, if you get an op-amp, minimum you will need 4. You need 5. You need 5 terminals so that you can connect inputs, output, power supply, and a ground. Now, if your input and output share the ground, right, that's how you do it in this op-amp. If they don't share the ground, you might need another terminal, but most of the time they'll share. If you have multiple op-amps or same circuit, they can all share the same ground and power supply. So if you say have 2 op-amps, you don't need like 10 terminals. You only need 5 plus 3 more. So that would be 8. That's how you make the connection. All right. Also, the op-amp, ideal op-amp has a couple of unique properties. The input resistance is infinity. So that is a property of ideal op-amp. When we say input resistance infinity, you can derive saying, well, it means that the current flowing to the terminals are going to be 0. So that's basically what we can derive from what ideal op-amp means. Okay. And the second property is for ideal op-amp is gain is infinity. Now, when a gain is infinity, what we can derive from that is important. The infinity gain itself doesn't mean anything because we don't use it anymore when I say ideal op-amp. What we derive from there is what we say is V plus and V minus is going to be the same. So the 2 terminals, you look at the plus and minus terminal, those voltages are going to be the same. That's the reason why, because our gain is infinity and our output is A times V plus minus V minus. Because your gain is infinity, for any given output, VO, the input must be 0 because you have to have a 0 multiplied by infinity to get a fixed number. When you get the limits, right? That's how you do it. The limitations, right? You get a infinity multiplied by a near 0, and those 2 have the same order, and then you get a fixed number. So those are the 2 properties. And also, there's one more is output resistance 0, and we don't use that much for now. So this is what I said previously about adding power supply to the terminals, and then you have positive is connecting to a voltage supply, and the bottom is the ground. You connect that to ground, and you have 2 input terminals, and you have output terminal. In this particular drawing, you guys notice that we flipped the plus and minus sign. Instead of plus sign on top, we have the minus sign on top of the op-amp. This is very typical. When we use op-amps, we put minus on the top part of the op-amp. So when you do your homework or when you do your exams, pay attention to where the minus sign is. It might be to trick you. They might be tricking you to put the minus sign at the bottom instead of the top, and you have to be careful so that you don't make a mistake on that, because that can determine a lot of stuff. And then the right hand is a complete drawing showing the ground in the middle, and then the power supply range for typical op-amp is about 15 volts, minus 15 to plus 15. Yeah.
And what you said about the minus, plus?
Yeah, do you see the minus sign and plus sign inside the triangle? Yeah, sometimes they flip it. Okay, they mirror it. Like, okay, this one also. But sometimes they do it like this. Sometimes they do it. Have the plus minus sign exchange.
And would the power supply have to change through?
The power supply is merely just a connection, so you can do whatever you want, right? But of course, in this case, you can still do power supply here, and you can do ground here. But of course, you can flip it as well. It doesn't matter. Yeah. As long as you mark them properly, it's no problem. Okay. So for ideal op-amp, or non-ideal op-amp, the equivalent circuit, a lot of times we say, okay, now you have input, you have output, you get a triangle, and what exactly it represents. So this is the equivalent circuit. You have input, two terminals. Input resistance is infinity, which means the open circuit. So between terminal minus, terminal plus, the infinity resistance, open circuit. And output is a voltage, A times the difference between the two inputs. And output resistance 0, so there's no resistance at the output. So therefore, you really have just A times V2 minus V1, that's your output. But when A goes to infinity, so apparently, as we said, you got V1 and V2 are going to have to be the same. Now, of course, you might say, okay, if I actually have two voltage sources at the input, how can you say they're the same? If you actually have two input voltage at the input, they're not going to be the same. Okay. Now you're going to see later on, we can add a resistance between your input and the terminal, and you can still make the two input terminals voltage the same. So which means if you have if we have say a voltage here, and if we have a voltage here, and we have a voltage here. So in this case, V plus and V minus is still going to be the same. But in the case here, unless unless you change it, otherwise, unless you have the two terminals voltage are the same, otherwise they're not going to be the same. So we amplify the difference. Okay. So now let's start to solve the problem. I think you guys already learned this in 2 times, but anyway, we're just going to we're going to like still look at some of this. So for inverting amplifier, what we're doing is we're connecting the input to the minus sign of the input, which is often called an inverting input. And then the positive sign is a non-inverting input. So there are two inputs, input terminals. And then in this example, we ground the non-inverting terminal, but we put input at the inverting terminal. And then we connect some resistances to the circuit. So given the principles we just discussed earlier, we can start to look at what happened, how to solve the problem. Again, this example A is infinity. And you can see that you guys can work together. So V plus is 0, right? Because V plus is grounded. So let's go to V plus here. V minus. So V plus 0 is by observation because it's grounded. So let's do step by step. So number 3, let's say the principle that we had is that the two terminals are going to have the same voltage, which means that's what by applying a principle, therefore it's going to be 0. So that's basically we derive from the definition of op-amp. The two input terminals have to have the same voltage. So now you got that. Now since V minus 0, we can calculate current. Okay, we can calculate current II. It's going to be let's call it VI minus V minus divided by R1. Oops. It's too sensitive. Okay, so we're gonna have to say I equal to this. So we got to the current. So the next principle that we're gonna apply is I minus equal to I plus equal to 0. This is also derived from the property of op-amp, saying that the input resistance infinity, therefore there's no current flowing into any of the terminal. So you get that. So once you get that, and the next step will be easy to find out, okay, we're going to have I2. How much is I2 going to be? Can you guys figure out? It's going to be same as II, yeah, or I1, yeah. Let's call it II. Right, so that's going to be Vi minus V minus. V minus basically 0 divided by R1. Yeah, it's equal to Vi divided by R1. So we got that. So now, what is the current actually? So let's go to number 7. Is how actually going to calculate current I2? If you look at the resistance of R2, basically there's voltage V minus, there's voltage VO, right? So the voltage drop across R2 is going to be current times resistance. So what it really means is that I2 is actually going to be V minus minus V0 divided by R2. So in this case, V minus 0. So therefore, we have I2 equal to minus VO divided by I2. Or we say VO is equal to minus I2 times R2. And we're going to plug in this bottom line here. We're going to plug in this here. So we get VO equal to minus R2 over R1 times Vi. Vi is the input. So now we got output is proportional to the input, but there's a negative sign. So to understand the negative sign, you know that current has to flow from a higher voltage to a lower voltage, right? Now the current actually I2 is flowing from V minus, which is 0, to VO, which VO must be lower than 0. So that's why VO is negative. Yeah. Is it clear? It's very simple, guys. Remember, infinity gain, input current is 0, V plus and V minus has to be the same. You got those? Then you can solve any problem. So this is actually step-by-step how to solve the problem. We can skip that. Yeah, so this is just step-by-step. We did that already. Okay. Now let's do another example. This circuit apparently looks much more complex than the previous one. Got multiple nodes, multiple connections. Yeah, so let's see how we can do that. Again, this is ideal op-amp. So we're going to do step 1 is A is infinity. And step 2, we're going to say V plus and V minus is the same. I'm going to jump one step. Why is 0? Because V plus is grounded. So V plus 0. So V minus and V plus, they're going to be both 0. That's the second principle. So then, number 3, we're going to look at, what do you call it, II or I1? Okay, let's call it I1. So I1, we can easily calculate. It's going to be V1 divided by V1 minus 0 divided by R1. It's just V1 over R1. We got a I1. And then I2, because current going through into the terminal minus terminal 0. So if you look at the node, right? You look at the node between R1 and R2. There's no current going into the op-amp. So therefore, I2 equal to I1. Okay. So now, can you find Vx based on our previous example? You should be able to find Vx easily because Vx is going to be minus I1 times R2, or R2 times R2, which is equal to minus I1 times R2, which is equal to minus R2 over R1 times V1. Right? So again, current flows from a high voltage, which is 0, to a low voltage, which is negative. So R2. And at the node X, we can use nodal analysis. Like in this case, we have I2 plus I3 equal to I4. Right? So with that node, you have 3 currents, 2 coming in, 1 come out. So that's easy to understand the nodal analysis. Now we already have I2 we've already found I2, and we need to find just I3. So I3 will be 0 minus Vx divided by R divided by I3. And also I4 will be Vx minus Vo divided by R4. So now you can plug in R2, R3, and R4 all back to the same equation. How many variables do you have? Because Vx, we already found it. R are constants. V1 is given, the input. So you only have one variable, which is VO. So you can find the VO. So I'm going to skip the exact results that you guys can find it using your math skills. Okay. So the previous example, we can also change it to a current amplifier. With the current amplifier, we would just replace the voltage source with a current. So this input is a current instead of voltage. Now, for this input of current, the way that do this is very similar. So again, A is infinity. Okay, so you get A plus, A minus is 0. And then you have V plus equal to V minus. And they are both going to be 0. So those are the kind of derivatives from op-amp property. You can write them down right away, so you don't have to look back later. And then so here, when you have input current I coming into the terminal, again, if you look at the node at the negative terminal, you have 3 terminals, but one terminal has 0 current. So what it means that the other 2 terminals must have the same current. So therefore, you can easily conclude that I2 equal to I1. So once you have I1, you can say, okay, look at, you can easily say calculate Vx, or if you don't calculate Vx, actually you might write a nodal equation here, and then you can still solve the problem like what we did before. The nodal equation will be like I2 plus I3 equal to I4, and similarly you have I2 is given, and I3 is going to be, that's 0 minus Vx divided by R3, and I4 equal to Vx minus Vo divided by R4. But here we have to calculate Vx. So Vx is basically equal to minus I2 times R2. Now, why minus? Again, look, the current has to flow from a high voltage to a low voltage. The negative terminal is grounded. So therefore, Vx has to be negative. And so I just keep repeating this, you guys, later on, because we got a lot of this saying, oh, why is it negative? And if you start with a positive number, the actual number is correct, but the sign is wrong, and you will not be able to complete the problem to get the correct solution, right? So, okay. Yeah, so this is actually how we did it. We're going to go skip that one. And for this example, if you have a input without like the complicated circuit, like if we have input here, and we can, so from here, let's A. If we have input there, now you can see that V minus equal to V plus is 0. Again, that's given because V plus 0, so V minus 0. And also I minus equal to I plus, they're both 0. What I'm saying is inside here, like I minus, I plus. Those are 0. So therefore, we have I2. Oops. So we have I2 equal to I1. Let's call this I1. So therefore, we have VO equal to I2 times this 10K, and then we add a minus sign. So this kind of very simple current amplifier. You got a current input, you translate the current into a voltage output. So transferring current into a voltage. So the B is an equivalent circuit of that, because you have 0.5 milliamp coming in, you got voltage output. So this actually are going to be equivalent to each other without the amplifier. So like amplifier already transfer the voltage into a current source, transfer the current source into a voltage. Now, one more example, we jump to the next, is that the previous examples, we had VO. All the R1, R2, R3, R4 are part of your circuit design. We did not have a load connected to the output, which means, yeah, we've got an output, but we didn't use it. So now we're going to use it. How do we use it? You connect a load. If it's, for example, audio amplifier, you would have a speaker connected at the output. Okay, if it's some say pressure amplifier, now you want to drive a pump. So now you're going to connect your pump at the output. So in this case, what we did is we connect a 1 kilo ohm resistance. So this 1 kilo ohm, we call this load resistance. RL is a load resistance. So this is RL. Let's call this R1, R2. So if we plus is 0, and then we minus, it's going to be 0. So let's call this number 1. Step number 2, because we minus 0, so we have I1 equal to 2 volts divided by 1K, gives you 2 milliamps. And number 3, we say we minus. So you have trouble in the future to figure out whether it's positive sign or negative sign, or negative output, positive output. You can always do this. Just take the voltage difference, divide by this 5K, that gives you I2, right? And I2 equal to I1 equal to 2 milliamps. So therefore, because we minus 0, so therefore we have VO equal to minus 2 milliamps times 5K 10 volts. Should be $5K equal to minus 10 volts. So by this time, you guys probably understand why we call this an inverting amplifier. Because input is positive, output is negative. That's called inverting amplifier. We are inverting the input from positive to negative. It's called inverting amplifier. To get an inverting amplifier, you always have to have a power supply. So which you have, in this case, you have a power supply. You have to have a positive power supply, say 15 volts, a negative power supply of minus 15 volts, and then there's also a ground. Without a negative power supply, you will never be able to get a negative output, that's for sure, because that output is actually supplied by your power supply. All right. We can go from single input to more complex circuit. In this case, we have 3 inputs or more than 1 input. The principle is still going to be the same. What we're doing is we're going to say V plus 0. That's something you can derive. You can observe. Therefore, you can conclude that V minus 0. That's very important. V plus V minus are the same. If without this, you can't solve the problem. Okay. And the second step is to find the current. Now, for each branch, you have V1 coming in, and this node is a supernode. The supernode have a voltage of 0 volts. If that voltage is given, can you calculate the input current of each branch of input? Yeah, should be fairly simple. So we can calculate I1 equal to V1 minus 0 divided by R1, which is equal to V1 over R1. Well, I2 equal to V2 divided by R2. And then we have IN equal to VN divided by RN. Okay, so we find the current because one is input voltage, the other terminal is 0. We have resistance be 10, so it's almost all. So next step is that there's a super node. You have multiple current coming in. How many? There's only one more line that connects to the on the left side. Of course, there's one into the op-amp which has 0 current. So therefore, we can find current I. In this case, it's going to be I1 plus I2 plus IN. You have all currents coming in from the left hand. You have one current coming out from the right hand. Right? So very simple nodal analysis you can do. Once you find the current of I, we can now do the final step is find VO. Now to find VO, we can write I equal to 0 minus VO divided by RF. So therefore, we have VO equal to minus I times RF. So when you plug in all this number, you will get the final expression of VO equal to the RF over R1 times V1, RF over R2 times V2, da 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 da. So it's so because the final solution is addition of all the voltages, so we call this addition, adder, like you add stuff. If R1, R2, R3, and Rn are all the same, you add them basically proportionally. If they're not the same, so each has a weight. Like maybe one is added 50%, other is 1%, depending on the resistance of R1 to Rn. So this is addition. And okay, so next we're going to look at multi-stage. So multi-stage, by its name, you have two amplifiers. Stage 1, and then the output of stage 1 feeds the input of stage 2, and then at the output of stage 2, you get your final output. So in this case, for stage 1, you guys probably know already how to do it, so we're going to neglect. So basically what we're saying is we got V1, let's say VO1 here. So we can write together without going all the complex steps. Can you guys write together? How much is VO1? Don't forget the minus sign. That's 1. And then we're going to have over R1 times V1 plus RA over R2 over times V2. That's all VO1. Okay. Now the VO1, we have multiple input with 2 inputs. We get the output at VO1. Now we have stage 2. So for stage 2, how many inputs do you have? 3. So this is also adder. So you would say, okay, VO equal to basically VO1 divided by, again, don't forget the minus sign. VO1 divided by RB plus V3 divided by R3. This is VO1 times V2 or V3 plus V4 over R4 times V4. So you got the second stage output, which again is also negative. So depending on the value inside the parentheses, your output can be like, can be anything because the first stage output is negative. So if it's a negative is very big, it's going to cancel the other two, right? So the second is V3 and V4 is positive, but V1 is actually negative, right? So you have one negative with 2 positive, so combination, you get any kind of numerical value for your output. Okay. Yeah.
For VO,
yeah.
Shouldn't it be the resistance RC divided by
RC? Oh, yeah, you're right. Okay, thank you. Okay, yeah, you're right. You're right. Thank you for that. It's very important. Oh. You're right. Sorry, it's RB. No, RB over RC, and the RC and RC. Yeah, yeah. Thank you for that. I made a mistake. Anything else? All right. So much about inverting amplifiers. Inverting amplifiers is important. It's simple, but sometimes we do need to get non-inverting amplifier. The non-inverting amplifier has two advantages. One is that the output is positive, so it's easier to use. So above ground. A second advantage is that you don't need a negative power supply. So you get the input, you get the output, so you only need one power supply. Like in this case, you only need one power supply, positive. You don't need a negative power supply. So this is a good stuff. So that's why non-inverting amplifier often is also quite popular in IC design, because we don't want a negative power supply. It just add complex, add cost, and add volume to your design. So for a non-inverting amplifier, basically you're going to also use the, I think it's like two principles. One is that V plus V minus always the same. Two is current going into the terminals are zero. So those are things that you remember. Now you can do it. So in this case, when we say the minus and plus sign, the minus and plus input terminals or inverting and non-inverting terminals have the same voltage, we don't mean they have to be zero. Okay, it depends. It depends what's connected. Like in the previous example, we always had a zero, but no, they don't have to be zero. It can be anything. It depends on the circuit design. Okay. Now, so we jump to this example. You look at it. What is V plus? It's V1. Yeah, it's basically it's given. Right? It's right there. It's V1. So from here, what is the voltage at V minus? It's not plus. It's V1. Okay. So if that's the case, we move on to here, so which means this is also V1. So this is V1. I want you to look at what is the current I1. You note the direction that I draw the current going to the left direction. Why did I do that? It's just like for your, it doesn't matter which direction you put it. But if you put it in the way that it can make your life a little bit easier, that's all. So in this case, I'm putting them to the left because I know that at the inverting terminal, there's a V1. And on the left hand, there's a ground. So if I put it that way, I can easily calculate I1 to be V1 over R1. That's the only reason I do that. Okay, now in order to find VO, first of all, let's find I2. So how much is I2? Well, you know that the current going into the terminal, into the input terminal is zero. Therefore, I2 is going to be same as I1, which you can further write it as V1 over R1. So how do you calculate R1 in this case? How do you calculate I2? Well, I2 is the current through R2, and it got a voltage drop when current flows. And that voltage drop is the difference between the right hand and the left hand, because current flow from right to left, right? In way that I mark. So what it means is that we're going to have VO minus V1 equal to, clear? Right? So voltage difference between right and left side of the resistance equal to the voltage drop on that resistance. So from here, we can find that VO equal to R2 plus V1, which equal to and I2 equal to V1 over R1. So we have V1 over R1 times R2 plus V1, and we simplify this one, can be 1 plus R2 over R1 times V1. So we get the final expression for the voltage output. If you look at it, you'll find that something that is different from what we did before. First of all, is the negative sign. So the output is positive. Input is positive, output is positive. Therefore, it is called a non-inverting amplifier. It's not inverting because output and input are having the same symbol, same polarity. That's number one. Number two, the ratio between input and output is not exactly R1 R over another R anymore. There's one plus over there. So basically, when you amplify the input by a ratio from R1 to plus 1. So whatever that ratio is going to be, if the ratio is 1, your ratio is your gain is 2. If your ratio is 10, then your gain is 11. So here I want to introduce like a definition. Is usually we call this one a voltage gain. So in this case, we have 1 plus R2 over R1, and we use a unit of voltage, volt per volt. So it's a voltage gain, which means if your input is 1 volt, your output is 10 volt, you get a gain of 10. So basically it's unitless because it's voltage by voltage, right? So 1 volt to 10 volts, so the gain is 10. So it's called a voltage gain. We use this quite frequently in the future, but that's something that you can. Okay, so the next slide is looking at step-to-step analysis of that. And finally, for the different amplifiers, we have what we call a unit gain buffer on top. It's a unit gain buffer. Why is it called unit gain buffer? Because if you look at V plus, you know that V plus is equal to what in this circuit? Equal to V1, okay? And then what is V minus then? V minus equal to V plus. That's by definition. So what is VO? Well, V1 and V minus are connected by wire. Okay, so VO is equal to V minus equal to V1. So output, input, same. In some cases, they also put a resistance here. I want to ask you guys, if I put a resistance here, does it change the output? Do I get a different output? Yes? No? Okay, we need to vote. How many do you think we will get a different output? Raise your hand, please. Minority? Okay. How many of you think we're going to get the same output? Raise your hand. Minority? So what is the majority? Uncertain, I guess. No. See, if you look at the resistance, even though there's resistance, how much current is going to flow through that resistance? 0. Because current cannot flow into the terminal. If current is 0, what's the voltage difference between on the two sides of the resistance? 0. Voltage drop 0. The voltage drop 0, your output doesn't change. So your output does not change with the adding resistance. Okay. Good. Now, a good question to ask. If input and output is the same, why do you want to do that? Input 1 volt, output 1 volt. What are you doing here? Why do you need that buffer? Yeah? For impedance. Okay, very good. Yeah. Okay, so it is basically for impedance. Why? I'll give you an example. Let's say you have a voltage source. Vs, you have Rs. And let's say Vs is 1 volt, and Rs is going to be 100K. And this is very typical. You get a sensor, the pressure sensor, noise sensor, whatever. And you measure the voltage, yeah, open circuit. But then you measure this internal resistance, we call source, something called source resistance. This resistance, and it can be different for different type of input device. Sometimes it can be quite big. So if you have that resistance, now you want to connect that thing to your say audio amplifier. You connect to a speaker. Then your speaker is so. How much current would you get in this case? Very simple circuit, guys. Let me know. Right. So you have 1 volt divided by 100K plus 1K. And what is the voltage then? Well, you can also do this as a voltage divider. So basically, what it means is that we can do this as a voltage divider, which is 1K over 100K plus 1K times 1 volt. And then that gives you roughly 0.01 volt. Do you see a problem? You get a 1 volt input, and you connect to your load. You only get 1% of your input. That's not good. That's not good. So what do you do then? That's where the unit amplifier works. Well, with unit amplifier, what you're doing is, oops, what happened? Okay. So with unit amplifier, yeah. Now we have a unit buffer, a unit amplifier. Then we have, forget about the resistance on the top. It doesn't matter because it doesn't change anything. So how much voltage do you get now with VO? With the input, still 1 volt? So you got a VO at 1 volt because it's a buffer, it's a gain. You need a gain buffer, right? You got input coming in at the positive terminal and negative terminal same, no current flowing, therefore your output is 1. So how much current do you get now? So VO over RL, you get like 1 volt divided by 1K, you got 1 milliamps. You got 1 milliamps. But if you look at the previous example, you got 0.01 milliamps. Only 1% of what you get. So this is why we use unit buffer, because we want to increase the input resistance to infinity, and we reduce output resistance to like 0. So that's really useful. Usually, when you design a multi-stage amplifier, the last stage is a unit gain amplifier. Okay, it doesn't have to be like op-amp. It can be just a transistor amplifier that gives you the last stage will be a unit gain. Unit gain. Okay. We can also have multiple inputs for our non-inverting amplifier. The principle is basically the same. In this example, however, we need to be a little bit careful, is because we don't know V plus, and we don't know V minus. One of the cases when students look at this problem, the minus sign is connected to ground through 1K resistance. Maybe that's 0. Well, if the current is 0, yeah. But if current is not 0 through R1, then what is not 0? Can the current be V2 or V1? or can be something else. What do you think? V1 is equal to V2? No, no, that was the input, so they are different. V1 plus V2? No. Look at the circuit. At the bottom or at the plus sign, how many branches do you have? How many branches? No. 3. Do you have 3 branches? Yes, you have 3 branches, right? There's 1 node, 3 branches. Now, among the 3 branches, we know 1 branch does not have current, correct? So if that branch does not have current, basically you can ignore it. So if you ignore that, oh, I just said we ignore it, so let's ignore that. Oops. If you ignore that, what happens to that circuit? Okay, so if I further draw this a little bit further, let you guys to recall what you learned. Was that better? Would that be better? You understand? You have 2 voltage source, you have 2 resistance. What are they doing? In the same loop. Same loop. Okay, if they're in the same loop, can you find the current? So you can find the loop current. Let's call it I1. So you can find I1 equal to basically V1 minus V2 divided by R1 plus R2. If they're both like positive like this, you go through loop. V1 minus V2 divided by the loop resistance, right? You got that. So you got I1. So if you have I1, which means this I1 coming this way, this I1 coming out that way. So now step 2 will be to calculate the voltage at V plus. How do you calculate V plus? Well, we know, again, if you guys have trouble figuring out how to calculate in 1 step, you can always do an intermediate step. We know that V1 minus V plus divided by that R1 equal to I1. So let's call this R1, R2, R3, and R4. Okay. So if you do this, you will find, because V1 is given, and V plus is I1 we solve already, so we can easily find V plus equal to V1 minus I1 times R1. So you got that. So you got V plus. So this is simply doing this little loop analysis to find your voltage at V plus. So once we find a V plus, you guys probably know how to do this. The next couple steps is V minus equal to V plus, and then you have let's call it I3, I4. So you got now you got it 3, and you got number 4. You say I3 equal to 0 minus V plus, this is V plus, divided by R3, and number 5 is I4 equal to I3. Yeah, that current goes, right? There's nowhere to go, okay? So now you get, last step is your V minus VO divided by R4, that equal to I4. So from here, you can find your VO, get some sort of expression, you can do it. So it's basically, I think for a lot of students, the most difficult part is to figure out how to solve for V1 in the initial step, because that looks a little bit, like when you guys say 0 and V1, whatever. Yeah, that's something you just have to be careful. Okay, so this is a numeric example. Yeah, so probably I don't have to go through this one. I mean, if you guys want to do this, you see, you can sometimes just simply write it on the diagram. You say, okay, so this is 1 volt. So therefore, there's 1 volt here, so 1 volt here, 0 here. So it's 1 milliamp, 1 volt divided by 1K. And this 1 milliamp over here. And then this is 9 kilo ohms. So therefore, this will be 9 volts plus 1 volt equal to 10 volts. This is the example that we did before. So you don't even have to write all these steps, to get this solution, because you can clearly mark them on the diagram where they belong to. Okay. So I think today we're going to also cover this differential amplifiers just a little bit, and let's see how many slides. Yeah. So often in real life, often we need to measure something that is a difference, not the absolute value. One of the typical example probably I can give you is that, let's say you have a bunch of battery in series to get the voltage you want. And each of this battery give you the 1.5 volts, and you 1, 2, 3, 4 in series. You get 6 volts, we have 4. Now, if you want to make the voltage of the whole 6 volts, you can always have a ground on the top. But what happens if you want to make the voltage of the middle set? This is quite useful. In the middle one, there are actually 3 of them. The top one, 2, 1, 2, 3. The 3 of them, you want to make the voltage of that single cell. How do you do that? You cannot use the op-amp, because op-amp, one of them has to be grounded, so it doesn't work. So therefore, we use what we call a differential amplifier. So we would put the input across the 2 input terminals. We take the difference, and usually the input and output has to be isolated, so they don't use the same ground. Because if you use the same ground, you'll be in trouble, because they say you have another one. Right? So you see the bottom input and the upper input of the second one, they share the same terminal. So if they share the same ground, you're basically making a short circuit. So it's not going to work. So all this, what we call like isolated amplifiers. But in general, a lot of op-amps will let you take the difference of 2 different voltage sources as the input, which means they can share the ground. They share the ground, but you can take the difference. So that one is what we call is okay. Let's go on with some examples later. So in this case, we have input, and we also have within the input, you have positive half and negative half. We call that a difference input. And then you have also the voltage, the same voltage in the middle. That's called a common mode. So the idea is to connect an input like this. So if you look at this input, this one, because remember we talk about superposition, right? If you have a 3 voltage source as input, when you do solve the problem, you can do one by one. You can use superposition. When you do one by one, you simply short the voltage source and open the current source. In this case, we have all 3 input voltage sources. So therefore, we can do like 1. So if we do this, what happens? You see the 2 input terminals have the same input. Well, in this case, your output ideally will be 0 because anyway, but if your op-amp is not ideal, and then your output is not 0. Actually, it's going to be a little bit of output. So that's called a common mode output. But again, that's only when the op-amp is not ideal. If it's ideal, you get 2 identical input, the difference is 0, the output is 0. So that's called a common mode. And then you have differential mode. So basically, when you have a differential mode, right? And we short the common mode. We short this one. So we short this one. If you look at, you have input to one terminal, you have another input to another terminal. So therefore, what you're doing, you take the differences between the 2 inputs, basically, because your output VO is going to be A times V1 minus V2. You're taking the differences. If A is not infinity, if A is infinity, apparently those 2 somehow have to be the same, and we talk about that later. So this is very important when we talk about differential amplifiers. But differential amplifiers, in this case, they share the ground. We cannot use this one to measure the voltage of the string of batteries. You want to measure the voltage of the middle one? No, you cannot use this. All right. So this is a very typical differential amplifier, or sometimes called a difference amplifier. And as you can see, as we move on to this problem, you will see that it is going to the output is going to be a multiple of the difference between the 2 inputs. So how do we approach this problem? So you go back to think about op-amps. What are the unique properties? Well, the unique properties is that V plus and V minus are going to be the same. Again, not necessarily 0, okay, unless one is connected to ground, otherwise they may not be 0. And number 2 is I plus I minus 0. So which means we go here, that's 0 amps, that's 0 amps, that's V plus, that's V minus. So those are the principles that we have to follow. So based on those principles, sometimes we apply one before another. So it really depends on the circuit configuration. You might be using the current 0. And if you go back to the circuit, you guys remember this one here is, no, this one here. What did we use the principle? Which principle we use first? The 0 current to the input terminal, right? That's how we use it. Right? Yeah. So here, which one do you think we need to apply? Which principle we need to apply first? Well, if we apply number 1, we said V plus is equal to a minus, which is okay, but we don't know what exactly they are. So that is a problem. So we need to look at the second one because we couldn't find anything. So we need a second one. So the second one says I plus and I minus both 0. So if they're both 0, look at the bottom, look at the plus sign. What do you have over there? Again, this terminal has, this node has 3 terminals, but one terminal has 0 current, which means you have like this. That's the circuit you have. So with this circuit, can you guys find the voltage over here, which is the voltage V plus? So that's what we need to find out. This is the voltage divider. Very simple, right? So we can write as R4 over R3 plus R4 times Vi2. We got that voltage. Now we can apply the second principle. The V minus equal to V plus. Again, it's going to be the same, R4 3 plus R4 times Vi2. So once we find V minus, I need to find I1, and then of course I need to find I2. But I1 equal to what? You see, that's V I1 minus V minus divided by R1. So you can plug in this one to this equation, you get the actual value of I1. Next step will be finding I2. I2 is going to be the same as I1. All right, so another I1. And then last step is to find VO. So in this case, we can write, in fact, so I2 equal to I1, yeah. So we need to find VO. So in this case, to find VO, we need to write this. VO minus VO equal to R2 times I2. So from here, we have VO equal to V minus R2 times I2. So now you can plug in all the numbers to get the final expression. I believe we have, I don't have the actual write up, but if you write the final expression, you'll find that your output is the difference between V1 and V2. So we call this a difference amplifier. We amplify the difference between these two. So by this time, you guys already learned. Let's review what we have. We have inverting amplifiers, output is negative, input positive. There's a ratio between input and output. We have non-inverting amplifiers, the output is positive, input is positive, output is positive. There's a ratio plus 1. And then we have additions. The output is addition of all kinds of input. Okay. And then we have multi-stage, which is the second stage amplified the first stage. Then we have unity gain amplifiers. And finally, we have this difference amplifier. We amplify the difference of the two input sides. So much, I think, probably reviewed a lot of stuff here learning to that, and probably a little bit more. I think we can stop here. The next week, we're going to finish the meta contents of this chapter. Our multi-stages, implementations, and integrators and differentiators. And then on fourth page, we're going to do a bunch of complex examples to get the better thing. So by the way,